Well, I think we're going to start now, and the next speaker is Daniel Grumiller from ITP and Technical University of Vienna. Well, a short introduction. So he did his PhD in Vienna with Wolfgang Kummer. Then he moved shortly for a couple of years to Leipzig. Then he worked in MIT for a couple of years. Then he returned to Vienna. And now he is associate professor in Technical University. And so he prefers to stay in low dimensions. But I think this talk will not be restricted to 2 or 3 dimensions, all right? So it will be in our physical world. And well, Daniel, please start.
Okay, yeah, thanks for the introduction. Also, thanks for inviting me. Fortunately, I have been a couple of times to Sao Paulo already, so it's not that devastating that I can't visit you again. So yeah, today I'm going to give a lecture on interacting black holes and near horizon symmetries, and it's going to be relatively basic. So I apologize to the experts in the audience for that. So I'll start with a very existential question, namely why study black holes in the first place? And in order to address this question, first I go into some physics history. So the first time somebody thought about black holes, at least the first time we know about it, was in 1783. That was Reverend John Mitchell. And it's not a coincidence that this happened more or less in this century, because you need 2 ingredients to think about black holes. One is Newton's law of gravity, which emerged in the previous century, so in the 17th century. And you also need the finiteness of the speed of light, which was also measured in the previous century. And John Mitchell was the first one to put these 2 ingredients together. And in this paper, part of which is quoted here, he concluded that all light emitted from such a body would be made to return towards it by its own proper gravity. So he was the first person to consider what happens when the escape velocity of a star exceeds the speed of light. Of course, this is not the way that we think about black holes nowadays, but it was the first time that this concept of dark stars or of objects that are invisible to far observers was put into some scientific paper. Okay, then for a long time, nothing happened in this respect, at least. And that changed in 1915, when shortly after the conception of general relativity by Einstein, Karl Schwarzschild wrote down a non-trivial exact solution of that theory. So besides Minkowski space, that's probably the simplest solution that you can write down. And it's quite remarkable that this is actually a black hole solution. So here's again a quote from Schwarzschild's original paper, which was called Über das Gravitationsfeld eines Massepunktes, so on the gravitational field of a point mass. And I'm going to elaborate on the Schwarzschild metric a little bit on the later slide. But I want to highlight the simplicity of this solution. And this captures of a feature of black holes that is, well, even true nowadays. It's not just incidental. Namely, black holes are in some sense the simplest macroscopic objects in our universe. They're characterized precisely by the same quantum numbers as elementary particles, namely by their mass, their angular momentum, and the charges. All right, the next 2 milestones are more recent. So about a century after the theoretical discovery of black holes, black holes were discovered in a merger through gravitational wave detections, or rather the other way around. Gravitational waves were discovered through a black hole collision that happened in our universe, and LIGO was fortunate enough to record this event. And here you see the famous LIGO data. So again, I'll elaborate a little bit more on this gravitational wave profile, but one characteristic feature you can see by just looking at this plot, either on the left or on the right, namely the frequency and the amplitude, they peak just around the merger, and then you have exponential decay of the gravitational wave amplitude. And this leads to this characteristic chirp signal. Okay, and well, even more recently, the first photo of a black hole, or rather of a black hole shadow, was taken by the Event Horizon Telescope. And I'm sure everybody in this audience has seen this picture already. And well, there's this saying, seeing is believing. So from this point on, I think there's no reasonable doubt about the existence of black holes because we're taking a picture of them. All right. Now, here are some more experimental reasons. So the first milestone from the phenomenological side that I mentioned here was the discovery and description of X-ray binaries and accretion disk physics. So this is displayed in this artistic rendering of a binary system. This is not what you actually see, but it is, well, how a disk would look like. So what's happening here is you have an invisible object here, a black hole in this black region that, is rotating in general. And then you have a visible partner, some star that is shining. And the black hole is accreting the mass that it sucks away from the star in this disk that is more or less in the equatorial plane of the rotating black hole. And it's also emitting jets. So there's a lot of non-trivial physics going on here. And at far distances, you can observe the X-rays emitted from this accretion disk around the black hole. And this was in the 70s and 80s, the main way of discovering signals from black holes, because by the very definition of black holes, they cannot be, well, they don't emit anything, at least not classically. So the simplest way to detect them is if they interact with something visible, and then you detect that visible thing, in this case, X-rays. And from the spectrum of the X-rays, you deduce properties of the invisible object, like its mass, its angular momentum, and perhaps other properties. Now, a more recent way of discovering black holes is by observing the Kepler orbits of visible stars around the black hole. So this was possible, for instance, for the supermassive black hole in our Milky Way. There is a video that shows actual physical data where you see these Kepler orbits, which are depicted in this colorful ellipses here. So if you click on the PDF, once it's on the webpage, you can look at this video. And I stress that this is a video of actual data, so actual observations made over a period of about 14 years, and not a simulation. Okay, but what you see from this picture, these are just standard Kepler orbits with sometimes very elongated ellipses, and they all move around the common focal point. And in that point, you have a black hole. And the reason you know it's a black hole is because if you had a collection of stars with the same mass, that collection of stars had to be much bigger than some of these elliptic orbits here. So the only object that has reasonable physical properties that we know and that can fit inside all these ellipses is actually a black hole. Okay, gravitational waves I've already mentioned. Again, in the PDF, you can click on a video here. And also black hole shadows I have mentioned. Since this picture looks quite different from the artistic rendering here, let me mention what the difference is. So this is how the accretion disk would actually be. So it is a disk in the equatorial plane of the black hole, more or less. But this is how the disk would look from far away. So in addition to what the disk is, you have to take into account light bending effects. And a black hole acts as a strong gravitational lens. So this is why you cannot hide behind a black hole. So the part of the accretion disk that you see that moves upwards here, this is actually the part of the accretion disk that is behind the black hole. But due to strong gravitational lensing effects, you can see it from a distance. Okay. So this was experimental milestones. Let me now address also 4 theoretical milestones. The first milestone is, well, largely due to Chandrasekhar. So he was the first person to think of a plausible mechanism how black holes could form abundantly in our universe, namely through gravitational collapse. So the short version of his argument is that if you have stars that are a handful of solar masses, then at some point when they can no longer burn hydrogen into helium because everything, well, has been used up, then the Fermi pressure, which stabilizes white dwarfs, so also other compact objects like neutron stars, is no longer sufficient to counterbalance the gravitational collapse, and the collapse will not stop, and the matter will collapse all the way into a point, into a singularity, and this is how you then form black holes. And the fact that Chandrasekhar was able to calculate this critical mass and found that it's of the order of a couple of solar masses shows that black holes are expected to be abundant in our universe just because our sun is a relatively typical star, and there are lots of stars that are slightly heavier than our mass, and certainly heavy enough that they will eventually collapse into a black hole. Another set of important theoretical discoveries happened in the 60s, shortly summarized the Singularity Theorems due to people like Hawking, Penrose, and others. And the main essence of these theorems is that singularities, which you find, for instance, in the Schwarzschild black hole, are not an artifact of some approximation that is made. For instance, the Schwarzschild solution is a very simple solution because it's spherical symmetric. So you may be worried about singularities being an artifact of these simplifying assumptions. But Penrose and others showed that given some assumptions about matter, about positivity of energy, and so on, once you have a region where you have so-called trapped surfaces, so basically something like a black hole horizon, then you can show that singularities always form behind the horizon. Okay, a more recent milestone, but still, from the 70s, was the merger of black hole physics with quantum mechanics. And that's the famous Hawking effect that shows that black holes are actually not literally black in the sense that they don't radiate anything, but they're only black like a black body. So they emit thermal radiation at the Hawking temperature. And the formula for the Hawking temperature is engraved on Stephen Hawking's tombstone. You can see it here. And its main content is that the temperature is inversely proportional to the mass. So the bigger the mass, the smaller the temperature. And practically that means that this radiation is, well, very hard or next to impossible to observe for the black holes that we know, because the temperatures of the order of nanokelvin, which is about 9 orders of magnitude smaller than the ambient temperature of the universe, which is about 3 Kelvin. Still, conceptually, it's a very important effect, and it led to the holographic principle eventually, which many consider to be our best approach to understanding quantum gravity. This talk is not going to be about holographic principle, even though most of my research revolves around this principle. So let me just state in one sentence what this is about. So the principle states that quantum gravity in d dimensions is equivalent to a quantum theory without gravity in 1 dimension lower, meaning that you can choose either the higher dimensional description, like in an actual hologram, or the lower dimensional description, the holographic screen, if you want. Okay, so the upshot of this slide is that black holes are now an established part of physics and of research, and they are relevant for astrophysics, cosmology, and classical and quantum gravity, and well, last but not least, also for science fiction. This is, of course, slightly less relevant, but it nevertheless had an impact on some aspects of physics, or at least of numerical simulations. So what you can see here is a picture of the black hole Gargantua that features prominently in the movie Interstellar, which was co-produced by Nobel Prize winner Kip Thorne. And what you see here is not some artistic rendering, but actual physical data. I mean, not physical data from our actual universe, but numerical data. So this is a numerical simulation of a black hole that, in principle could exist. It doesn't exist precisely in this form, precisely with this spin and mass and so on, and this precise composition of the accretion disk, but it's, well, not an atypical black hole. And you can see that the optical effects are, well, similar to what was displayed in the earlier pictures, and is also seen in the actual photograph taken of the first black hole. Okay, so let me address now some theoretical idealizations of black holes, because in order to provide a theoretical description of black holes, well, let's start with something simple. So the simplest assumption we can make is that we have an isolated stationary black hole in vacuum. And if we make this assumption and additionally assume spherical symmetry, then we end up with this Schwarzschild metric that I mentioned already. So in case you've never seen a metric, well, I hope you have at least seen the Minkowski metric. And if you set m equal to 0, then this is nothing but the Minkowski metric in spherical coordinates, with t being time, r the radial coordinate, and theta and phi the usual angles of the two-sphere. And if the radius is very large, then this again approaches Minkowski metric. So this is an example of a so-called asymptotically flat metric. But if m, which is the mass parameter, is not equal to 0, then this differs from the Minkowski metric. And in particular, you can see that at finite values, so specifically at r is equal to 2m, drastic changes can happen. So at r equals to 2m, this coefficient here becomes 0, and you get a coordinate singularity, and that's precisely the locus of the black hole horizon. And if r goes to 0, then you have an actual physical singularity. That's the locus of the infinite curvature region. So one advantage of this solution is that it's very simple. So you can picture the whole space-time in this Penrose diagram. So what the Penrose diagram does is it depicts the causal structure of space-time. So to read these diagrams, you have to know that light rays move on lines of 45 degrees. But distances are not faithfully represented in these diagrams. In particular, this line here, denoted by this script I, or in short, scry, scry plus and scry minus. So these lines here are actually infinitely far away from any physical point in the interior. And well, I don't want to address details how to construct these diagrams. It's not very hard, but I don't want to spend time on this. But you can see immediately the main feature of black holes just by looking at these diagrams, once you know that light travels on 45-degree lines. So if you are somewhere in this outside region here, then you can send a light ray on a 45-degree line all the way to infinity. So it will reach an asymptotic observer. If you take a mobile phone and send a signal into an outgoing direction, an observer that is very far away from the black hole can receive your signal. But once you're in the inside region, so that region up here is the black hole region, then no matter what you do, your signals will always end up in the singularity, and there's no way for you to communicate with the outside observer. So this, this cross here in the center, this is the horizon of the black hole, and once you have crossed it, there's no way of returning, and there's no way of communicating with the outside world. And that's a defining property of a black hole. You can ignore the left part of the diagram. So the they are an artifact of the approximation of being in vacuum. If you include matter, then matter basically cuts off the left-hand side of the diagram, but you still have to take seriously the outside region of the black hole and the inside region beyond the horizon, and also the horizon. Well, one disadvantage of the Schwarzschild metric that it's too simple for many purposes. So let's try to make it more realistic. So the first objection is, well, this is a non-rotating black hole, and basically all the black holes that we have observed so far have angular momentum, many of them really quite large angular momentum. So, okay, we can just add it. We can add angular momentum and we get a metric that is slightly more complicated, but not too terrible. That's the Kerr solution discovered in the 50s. The other objection is that these black holes have no charge. This is phenomenologically less relevant, but it's still easy to remedy. You can just add a charge and then you get yet another generalization in the Kerr-Newman spacetime. Another objection I mentioned already, half of the spacetime is unphysical, but you know, you can just ignore the half and consider only the physical half. But the next point is more problematic. So for many physical black holes, so for all of them that have accretion disks, vacuum is not a good assumption because there is additional matter around it, and you have to consider how the black hole interacts with the matter if you want to make contact to the data. So I'm going to comment on this on the next slides. So this is an actual severe problem from a technical perspective. But even if vacuum is a good assumption, so for instance, in the case of two black holes encircling each other and emitting gravitational waves, you are essentially in vacuum. But then stationarity is not a good assumption. And also here, I refer to the next slides. So yeah, for the classical detections of black holes, accretion disk physics and matter is crucial. Here is a picture from this paper where they made a simulation of accretion disks. The first accretion disk model historically is due to Shakura and Sunyaev from '73. And there's a lot of physics input that enters in these accretion disk simulations. So you need general relativity, you need magnetohydrodynamics, viscosity, plasma physics, and so on. So it's very messy. And so far, there's no good paper and pencil methods to derive pictures such as this one. And well, what you see in this picture is a black hole in the central region, and this accretion disk is plotted here in some density plot. So what is plotted is the logarithm of the energy density. And here's the color coding. So this is logarithmic scaling. So most of the mass is concentrated in a relatively thin disk. And you can see that at large distances, the disk gets tilted, but close to the black hole, it's not tilted. So the black hole affects the dynamics of the accretion disk. And well, the accretion disk is essentially what we observe from far distances. So we need to understand the physics of this. And for this, the interaction of the black hole with the surrounding matter is important. Yeah, again, there's a video associated with this. You can click on this LIGO link here to see the video. So again, in order to understand pictures like this and the gravitational waveforms, so far the best we can do, if we really want to extract the full gravitational waveform, is to do a numerical simulation. Even though there are a few paper and pencil methods that work perturbatively to some extent, but still the state of the art is to do numerical simulations. So the summary of the past slide is that for a realistic theoretical description of black holes, we need to allow for non-stationarity and possibly also for matter. In my talk, I'm going to focus, oh, sorry, there's a typo. So I'm going to focus on non-stationarity, and for the time being, I'm neglecting the possibility of matter. Okay, so what are the possibilities? We can do numerical simulations, like on the previous slides. One disadvantage of this is that this computationally very costly. So even the two-body problem, just 2 point sources in GR, that cost of the order of 100,000 CPU hours. So it's not a simple numerical simulation. And also you might miss insights that perhaps are deducible with paper and pencil. So sometimes you have some generic structures for which you may not need very complicated numerical simulations. And you may not get full insights if you don't have a paper and pencil derivation of the corresponding observer. Okay, so the other possibility is to make theoretical progress. I'll refer to this on the next slides. And I'll start, well, in honor of Patricio, with this paper here from the 1990s, so from 1994. So in fact, I checked that 22 of Patricio's 100 papers on Inspire have disk or disks in the title. So he was quite active in this field. And this paper here is the famous one, the most famous among them. So what he did in collaboration with Lemos was to find an exact solution that consists of a superposition of 2 axisymmetric stationary solutions, namely a rotating black hole and a thin disk of counter-rotating particles with 0 net angular momentum. And there were numerous follow-up papers and extensions of this. So this is quite impressive that you still can get construct exact solutions in this way. But of course, it's not the full story. I mean, as you see from the accretion disk pictures that we discussed earlier, the reality of these pictures is still far more complicated than this. But it's a good start. So the aim is to describe interacting black holes with some theoretical tools. And the main goal here is to drop all assumptions about symmetries, so including axial symmetry and stationarity, to describe generically interacting black holes. So it's a noble goal, but it's a bit daunting. So how to approach it? Well, theoretically, in the spirit of Steven Weinberg, you could say it's straightforward, just solve the Einstein equations. And if you can't do this exactly, put it on a computer. I mean, in principle, that's all right, but these are 10 nonlinear coupled partial differential equations in 4 dimensions. So they're just too hard to solve with paper and pencil. Fully realistic exact solutions also seem out of reach. And imposing symmetries is something that we would like to avoid. So it's unlikely to capture all the features that we need. You could try to do something like work in the far field approximation, but as you saw from this accretion disk simulation, some features of black holes and its effects on surrounding matter are only visible in the near horizon region. So we cannot work in the far field approximation in general. It misses near horizon physics. Now, if this doesn't work, you might go in the other direction, say, okay, perhaps we just use the full theory of quantum gravity, construct some black hole microstates, and use the interaction of those microstates with surrounding matter to get new insights. I mean, in principle, that might be viable someday, but we do not know them in general. In particular, we don't know the microstates of Kerr black holes. So this is something that is also out of reach at the moment, at least. Also, there are too many. I mean, there are 10 to the 10 to the 77 microstates for the smallest known black hole, and for the biggest one, it's of the order of Googleplex. So it doesn't seem practicable. So since this is so complicated, let's step for a moment and consider a simpler theory. So what I want to do next is discover some aspects that resemble these problems, or at least the problem that there are too many degrees of freedom, in a theory that we understand very well, namely electrodynamics. So how to describe electrodynamics? Again, theoretically, it's straightforward. Just keep track of all the point sources, the electrons and ions, and use the proper green function, and then solve this linear partial differential equations. And n here denotes the number of point sources. Well, in many cases, the practical problem is that you want to describe some macroscopic material, and then n is of the order between 10 to the 20 and 10 to the 30. So yeah, even in electrically neutral systems, you have lots of point sources. I mean, electrons and nuclei or ions. So this is not very practicable. But there's a more practical solution. You can do electrodynamics in matter that provides a coarse-grained description, and that's sufficient for many purposes. And at least you can gain some insights into what happens if you have electrodynamics in media. And quite often, the main effects are adequately captured by imposing suitable boundary conditions. So for instance, the microscopic structure of a material can often be summarized in fixing the chemical potential, so the T component of the abelian connection, at the boundary of the material. So for instance, Dirichlet boundary conditions for a conductor, Neumann boundary conditions for a dielectric medium, and so on. So what we intend to do here is to do something similar for black holes, namely to impose different boundary conditions at the black hole horizon, with the idea that this is supposed to capture essential features of the way that the black hole interacts with its surroundings. Okay, so therefore, what I want to do next is impose near horizon boundary conditions. So in order to do this, I'll start with a near horizon expansion. So we take some, for instance, 4-dimensional metric and expand it in this way. So let me explain what this is about. If we keep only the leading terms, then this line element here is basically a Rindler type of line element. So the ellipsis refers to these subleading terms and also to the rotation terms. So the coordinates that I'm using here have the following meaning. So t is some time coordinate. Rho is a radial coordinate chosen in such a way that rho going to 0 corresponds to the black hole horizon. So you can see that there's a Rindler type of 0 in the TT component of the metric. And that corresponds to the black hole horizon. And the region rho bigger than 0 is the outside region. So since we're only interested in what happens outside the black hole, we can confine ourselves to that region. Now, the coordinates xa you can think of as angular coordinates if you want. So these are the transversal coordinates on the horizon. So for instance, the azimuthal angles theta and phi in the case of Schwarzschild. This coefficient here, kappa, can be a function. So it's a function of t and the angular coordinates in general, and it's non-zero by assumption. And if it's constant, then this is just surface gravity of some stationary black hole. But in general, it can be time dependent, also angle dependent. This quantity omega AB is a codimension 2 metric. So this is the transversal metric. If you want, you can think about it as the spherical metric, which is literally true in the case of Schwarzschild. In the case of Kerr, it's also topologically a sphere, but it's no longer a round sphere. And again, this metric can be time dependent, also depend on the angular coordinates in general. And then these additional functions here in this off-diagonal part of the metric, well, they're just additional functions that characterize the interacting black hole and some aspects of how it rotates. And again, this can be functions of time and of the angular coordinates. So this is the near horizon expansion, but this is not yet fully specifying the boundary conditions. We still need to specify what is fixed and what is allowed to vary. And this is also where non-trivial physical input enters and some choices that you have to make. A simple possibility that is reminiscent of the canonical ensemble, so keeping fixed the temperature, is to keep fixed kappa. So the variation of kappa vanishes. There's some fine print, but let me not worry about this at the moment. Okay, so we keep fixed kappa, but we do not want to keep fixed everything. So let's allow to vary these other functions, the one in green, so omega AB, and the one in blue. And for later purposes, it's useful to recombine these quantities in this specific way. So P is essentially the induced volume form, so the square root of the determinant of omega, and JA is some combination of these functions that, well, is useful for later purposes. And allowing them to vary means that delta P is allowed to be non-zero and delta JA is also allowed to be non-zero. So that implies that the allowed variations of the metric here are given by this delta G mu nu. So the only changes compared to up here is that this kappa squared term is gone because kappa is kept fixed, and also rho doesn't vary, of course. And also this term 1 is gone. But other than this, it looks very much like the metric above, except that we replaced all these functions here by the variations. And now comes the first key step or key insight. This near horizon expansion is preserved by infinitely many near horizon killing vectors. Now, if you've never seen this, or if you've never seen asymptotic symmetries, this should come as a shock to you, because, well, I assume you're familiar with killing vectors, and if you are, then you know that there are only finitely many in finite dimensions. So if you want to impose the killing equation that the Lie variation of the metric along some vector field is 0, then indeed, in these space-time dimensions, you get at most d times d plus 1 over 2. So in 4-dimension, mostly 10 killing vectors. But here, we don't require that these vector fields preserve the metric. We only require that it preserves this near horizon expansion. So operationally, what this means is that the Lie variation of the metric is allowed to be either 0 or of the order of these fluctuations delta G min mu. And if you solve this equation, then you find the solution for the vector field. So psi is given by some function eta, which for convenience we rescaled by 1 over kappa dt, plus eta a dA plus order rho terms. And these are arbitrary functions. So that means there are infinitely many of these vector fields. So you get infinitely many vector fields that preserve this near horizon expansion with these boundary conditions. So again, let me stress that this is a remarkable result. There are infinitely many near horizon symmetries. And once you have symmetries, you would like to inquire about associated Noether-like charges. In this case, they exist. So there are codimension 2 charges, delta Q, delta meaning we can only determine the variations. So delta Q, depending on these parameters eta and eta A that appear in the asymptotic killing vectors, is given by this codimension 2 integral. So this is an integral over the horizon 2 sphere, or whatever the topology of the horizon is. Let's assume it's a 2 sphere. And then you have eta delta P plus eta A delta JA. So this explains now why I introduced these combinations of functions and call them just P and JA, because precisely those combinations appear in the charges. And you can determine the gauge variations from the near horizon killing equations. And if you do this, you see that P transforms like a scalar density with respect to eta A diffeomorphisms, and J transforms like a one-form density. So there's very simple transformation behavior. Again, if you see this result for the first time, let me add some remarks. So this is analogous to the Gauss law and the electric charge in electrodynamics, with the important difference that we have infinitely many of these charges. And you can derive results such as this using either canonical or covariant methods. And a nice summary is contained, for instance, in this lecture notes by Compere and Fiorucci from a couple of years ago. Now, the main difference to global Noether charges is that these are codimension 2 integrals rather than codimension 1. So surface integrals, not volume integrals. And the other big or relevant remark is that you only get the variation of the charges, not the charges themselves. So if you want to get the charges, you still have to get rid of the delta. So you have to functionally integrate this equation. And in some cases, this may be easy or straightforward, but in other cases, this may be impossible. So it's not always true that you can get charges, but you can, even if you have an expression for their variations. Now, these charges generate the Poisson bracket algebra. So if you act with the gauge variation with respect to eta 1 on a charge depending on eta 2, you can define a Poisson bracket in this way. And this closes into some structure functions. And in general, you can have a central term. So this is the generic structure of this Poisson bracket algebras of these surface charges. What the structure functions are and whether or not there is a central extension, that depends on the specific model and on the specific boundary conditions. But we're still not done. We still need to make some choices. In particular, we have to address the question, do the chemical potentials let me call these functions chemical potentials, eta and eta A, do they depend on the charges P and JA? And if they depend on them, how do they depend on them? And this is a choice you have to make. So there's no right or wrong. It's a bit like, choosing the canonical versus the microcanonical ensemble in thermodynamics. It's not that one is correct and the other is incorrect. It's just that one has applications for certain physical questions and the other has applications for other physical questions. So depending on the precise physical question you ask, you may want to impose different dependencies. So this is in fact where the physical input about the black hole interactions enter. So this is still non-trivial input that we have to decide on. One choice is particularly straightforward, namely to assume that eta and eta A are indeed chemical potentials in the usual sense, so they are independent from the charges. And in that case, you can just eliminate the delta from both sides of the equations and get an expression for the charges. And this was first done in this seminal work by Donet, Giribet, Gonzalez, and Pino about 6 years ago. But there are more general choices, and we addressed them in more recent work about 2 years ago in collaboration with Alfredo Perez, Shahin Sheikh Jabari, Ricardo Troncoso, and Celine Zwickl. And I want to discuss 2 examples on the next slides for such choices and also explain why we made these choices. Okay, so the first example leads to something I would call BMS near horizon symmetries. So let me explain the choice. So we rescale this chemical potential eta in the following way. So eta is eta labeled by S. S is some real or integer number. And then we rescale by p to the power s divided by d minus 2, where d is the spacetime dimension. I'm assuming here d is at least 3, which is, as Dima was hinting, quite uncharacteristic for me, but okay. So for application, you can insert d equals 4 if you want. And we don't change the other chemical potential. So delta eta S is assumed to be 0 and delta eta A is also assumed to be 0, but that means that delta eta actually varies. Again, there's some fine print. Let me skip this. So if you do this, you can again integrate the charges. So the charges are now slightly redefined. So these new charges P with subscript S are P again to some power that depends on S. And the charges then again take a similar form as before, but the algebra changes. So if you determine the Poisson bracket algebra from this relation that I showed you, then first of all, you see there's no central term. So you only get structure functions, but no central extension. And second, you see the following features. So first of all, P commutes with all other P's. So this is an example of so-called super translations. Has nothing to do with supersymmetry. It just refers to angle-dependent time translations. So you have infinitely many translation-like generators. Okay, so then J with J gives, well, a generalization of the rotation algebra. Sometimes this is also called super rotations, but the right-hand side gives non-trivial structure functions. And the super rotations with the super translations do not commute. They give something that, well, again, contains super translations, and the precise coefficients, the precise structure functions depend numerically on this choice of the number S and also on the dimension. So for S equal to 0, this recovers the results by Donet and collaborators, because in that case, the original eta is state independent. But for S equal 1 and D equals 4, this turns into a very well-known algebra, namely the famous BMS algebra, discovered by Bondi, van der Burg, Metzner, and Sachs in the context of asymptotically flat spacetimes. So in their context, this algebra appeared at infinity. What is remarkable here is that we find this algebra in a near horizon expansion. And I should say that this was quite a shock in the 60s, because originally Bondi, van der Burg, Metzner, and also Sachs expected that they would recover just Poincare symmetries, because it seemed natural to assume that the flat space limit of general relativity just gives you special relativity. But this is not true, apparently. You get much more than special relativity. You don't just get Poincare, you get Poincare augmented at least by the super translations, and if you want, also by super rotations. Okay, and for other values of the spin, you get a higher spin generalization of BMS symmetries in arbitrary dimensions. Good. So that was one choice. Let me now discuss a second example, which I call soft Heisenbergian. So what we do here is, again, geometrically somewhat natural. So we rescale now eta A, whereas eta is essentially unchanged. It's only shifted so that the charges remain integrable. But the way that eta A is changed, so by this inverse power of P, means that the associated charges are converted from one form densities into one forms. So that's why this is quite a natural choice to make. And again, we define the chemical potential in such a way that eta H and eta AH are assumed to have no variations. And if you calculate the charges, then, as I mentioned, JA gets rescaled by this volume form factor, and you get this simple expression for the charges, and JAH is now a one form rather than a one form density. Now, this seems quite a harmless operation, but it has a very profound impact on the algebra. So if you calculate now the Poisson bracket algebra, it's qualitatively different from before. So let me first address the term that is unchanged. P with P is still 0, so you still have super translations as before. Let me next address a term that is only marginally changed. So J with J is still non-zero and commutes into something that is linear in J. So, okay, that has changed a little bit, but not drastically. But the Poisson bracket between JAH and P has now changed drastically. Before there were non-trivial structure functions, but no central term. Here, this algebra is abelian. Well, not this algebra, but this bracket is abelian, but it has a central term. So that's a qualitative difference to the previous case. And for simplicity, and because I want to shorten the discussion here, let me assume that this quantity here, basically the curl of J, so the field strength, if you want, that this is 0. And this is true in 3 dimensions. So here I go again back to lower dimensions, but it's also true in 4 dimensions or higher dimensions if you have spherical symmetries. It would also be true for the Schwarzschild black hole. And if I assume that FAB is equal to 0, then this algebra is extremely simple. So you have P with P 0, J with J 0, and J with P gives the derivative of a delta function. And you can further simplify this by converting J into, charges Q. So this you can do locally because the curl vanishes. So locally, J is a D of something. And that leads to surprisingly simple algebra, namely the Heisenberg algebra. So now you get Q with P is just the delta, P with P 0, Q with Q 0. So that's as simple as it gets. Okay, so why did we call this soft Heisenberg here? So here's some historical notes on that expression. This expression was coined by Hawking in his last series of papers, together with Perry and Strominger in the years 2015 and 16. And soft hair was found as part of the Horizon Symmetries in this paper by Donegui, Ribet, Gonzalez, and Pino. And soft Heisenberg hair was found first in 3 dimensions in this paper with Hamid Afshar, Stéphane Détourné, Ward Merbis, Alfredo Pérez, David Tempo, and Ricardo Troncoso. And it was later then generalized to higher dimensions, higher spins, higher derivative theories, dynamical black holes. So it's a fairly generic and robust algebra. So let me explain the name. Why soft Heisenberg hair? I do this, inversely. So let's start with hair. Hair usually refers to the excitations of a black hole beyond the asymptotic charges, so beyond mass, angular momentum, and electric charge. And here we have this hair. It's labeled by infinitely many near horizon charges, P of X and Q of X. Heisenberg just refers to the fact that the near horizon charges P and Q obey the Heisenberg algebra. And soft refers to the fact that these physical excitations have 0 energy. So let me show to you how this happens and why this happens. So if we consider the near horizon Hamiltonian, this is the charge associated with unit time translations. And this turns out to be kappa times P naught in our theory. And the key aspect algebraically is that this generator here commutes with all the generators of the near horizon symmetry algebra. So if you generate Heisenberg excitations of some state, you can think of some abstract quantum state, doesn't matter what it is, could be the vacuum state, could be a black hole state. And then you act on, then you calculate its energy eigenvalue. So H on psi is just some number E times psi. Then you can generate descendants of that state by acting on the state with this, the quantum version of these charges, Q acting on psi or P acting on psi. But when you calculate the expectation value, or the eigenvalue, so H acting on Q times psi is the same as Q acting times H on psi because H commutes with Q, and H acting on psi is just E psi, so you get the same energy eigenvalue, and the same is true for P. So the excitations are soft because uncharacteristically, the Hamiltonian commutes with all the raising operators and also all the lowering operators that we have in our theory. So that's a specific feature of these near horizon symmetries. Okay, and the last physical statement I want to make concern the entropy and the near horizon entropy law. So if you express the Bekenstein-Hawking entropy in terms of the near horizon charges, then you find a surprisingly simple result. Namely, well, having set G Newton to 1, the entropy is just 1/4 of the area. Well, that's Bekenstein-Hawking. And this turns out to be just 2 pi times P naught, where P naught is the codimension 2 integral of this charge P of x. So it's the zero mode charge of this tower of charges P of x. Now, why is this remarkable? First of all, it leads to a very simple near horizon first law where you don't have any work terms. So dH is just kappa over 2 pi ds, and you can translate this into T ds. T is just the Hawking temperature, surface gravity over 2 pi. So this is amazingly simple thermodynamics. No work terms, no PDV or BDP terms. And in case you know the Cardi formula, this is its near horizon version. And it's much simpler than the original Cardi formula. So here's some technical details for the experts. So in 3 dimensions, the Cardi formula takes this form. So the entropy is 2 pi times essentially the square root of the asymptotic charges. And you can show that the near horizon charges that we constructed is related to the asymptotic Virasoro charges through this twisted Sugawara construction. And for the zero mode, essentially what you need to observe is just that L is quadratic in P. That means that the square root is converted into just a linear expression in terms of this P naught. And this leads to this simple, near horizon entropy law. And there is also some cardiology way of deriving this. So there's some generalized Cardi type of argument that you can employ to derive this result. And it's surprisingly simple and much simpler than any other Cardi-like formulas that I'm aware of. And remarkably, this again works universally even for higher spin black holes, which is quite surprising because for higher spin black holes in 3 dimensions, the analog of the Cardi formula is much more complicated. It contains nth roots where n is the highest spin that appears in your theory. So it's a very complicated Cardi type of formula. But in all these cases, it always turns into a linear formula if expressed in terms of near horizon charges. So let me summarize what we've learned so far. So our ambition is to describe black holes by imposing suitable near horizon boundary conditions. So we're working with the assumption that this is possible. So what works generically is that we find infinite dimension near horizon symmetry algebras. This, appears to be true regardless of the dimension of the specific theory and also almost regardless of the specific boundary conditions. I mean, unless you make them too rigid. What also seems to be generic is that you get soft hair excitations. Optionally, you get specific forms of these algebras. So you get this spin S, BMS algebra in the dimensions, or the Heisenberg near horizon symmetry algebra. I say optionally because which of these algebras, if any, you obtain depends on choices that you make, and those choices are dictated by physics input, not by mathematical consistency. So you can defend any of these choices, and you can also invent new ones that haven't been discovered so far. But which of them is useful depends on the precise application you have in mind. Let me just remark on the side note that this BMS SD algebra for higher spins has appeared recently in the context of high spin theories in this series of papers by Campilloni, Francia, and Heisenberg. It's a different Heisenberg, by the way, of course. Then another thing that appears to work generically is that the near horizon entropy law is so simple. It's linear in the charges, and there's an associated simple cardiology, and also an associated very simple near horizon first law. Now, these constructions appear to work for higher dimensions. So we did this analysis in Einstein gravity in arbitrary dimensions. In 3 dimensions, people investigated also higher derivative theories and higher spin theories, and the same conclusion holds. But it's not yet the full story. So the original ambition was to describe interacting black holes. The specific boundary conditions that I've described are still slightly too simple to capture effects like the capture of gravitational waves by a black hole. So for this, you have to further generalize the boundary conditions so that you can describe the absorption of gravitational waves that enter a black hole. And if you do this, then you discover also new effects that I won't describe now. I just mentioned them, so expansion and spin memory effects. And you can see these recent results in this paper together with Ahmed Adami, Sheikh Jabari, Tagilu, Yavatanu, and Celine Zwickl from just a couple of months ago. And the only formula I want to quote schematically from that paper is that the formulas for the charges slightly generalize in these situations. So it's like you have an open system or leaky boundary conditions. So the charges are no longer conserved in time, but instead the non-conservation of the charges in time is compensated by some outgoing flux. So you have if you want, a generalized conservation or non-conservation equation or flux balance equation. And effects like these were also investigated in the past in the asymptotic region, where people imposed leaky boundary conditions. So notably in this series of papers with Geoffrey Combert, Adrien Fiorucci, and Romero Ciccone, this was investigated in asymptotic contexts. Let me also add a speculation, which perhaps is compelling, but we don't know if it will really be the final word on this. So it is a logical possibility that Near Horizon software encodes some information about black hole microstates, at least in some semi-classical limit. And there's an explicit construction that realizes this idea, at least in 3 dimensions. And this was done in collaboration with Hamid Afshar, Sheikh Jabari, and Hossein Yavatanu in these 2 papers here. But we don't know if this works in 4 or higher dimensions. From a both phenomenological and theoretical perspective, an open question is, what is the optimal choice of the boundary conditions? And as I hinted, this may not have a unique answer. It's a bit like asking, well, what is the optimal thermodynamical ensemble? Well, okay, that depends on the precise question you're asking. You cannot claim that the canonical or the grand canonical ensemble is optimal. It's just useful for certain questions, and maybe for other questions, another ensemble is useful. So I expect a similar thing to happen here, depending on what it is precisely that we want to describe. Slightly different choices of these boundary conditions and of the state dependence of the chemical potentials may have to be used. So that means, on the positive side, that a lot remains to be discovered. And if you're a student, perhaps some of these things to be discovered will be discovered by you in the future. So since I'm almost out of time, let me conclude with a couple of last words. So I think it's fair to say that we've come a long way since this pioneering work by Patricio and collaborators to describe interacting black holes. And our perspective that I try to advocate in my talk is that we put information about the physics of the interactions of the black hole with its surroundings into the choice of near horizon boundary conditions, much like in macroscopic electrodynamics, or at least inspired by macroscopic electrodynamics. Okay, since I'm organizing this conference, let me switch gears for 1 minute and announce that Strings 2022 will take place in Vienna, which is very fitting because, well, this year's Strings took place in Sao Paulo. Unfortunately, it was just online, but it was still a fantastic conference, and we expect that it will take place live. So if you know, to the extent that you can predict anything in COVID times, if you look at the curves from past years, then June and July is always a local minimum in terms of COVID cases in most of Europe, including Austria. So it seems likely that this conference will take place in person. And if that's the case, it will happen July 18 to 22 in Vienna at the University of Vienna. And if you want to keep yourself informed, just bookmark this link here to the Strings conference. Okay, so with this, I'm done. Let me stop here and thank you for your attention.
Well, thank you, Daniel. Thank you.